Hi, my name is Jackie Yuan from New York University. I will be presenting our paper, Block-Based Learned Image Coding with Convolutional Autoencoder and Intra-Prediction Aided Entropy Coding. This work was done jointly with Haojie Liu, Deepaga Mukherjee, Balu Asumali, and Yao Wang. Here is an outline of our work. We adapted the variational autoencoder model for block-based image coding. We analyzed some effects when using the VAE to code small blocks, and we designed some methods to alleviate the loss in performance due to small blocks coding, and we present our results. Our work is based on the variational autoencoder model by Belay and a later improved version of the model by Minute. It uses a variational autoencoder to compress an input image into a latent Y. Then the latent Y is entropy coded into a bitstream. At the decoder side, the bitstream is decompressed and decoded by a decoder network back to the reconstructed image. In addition to this, the model uses a hybrid prior network and a context model to predict the mean and variance for Y, while Y is modeled as a Gaussian distribution. And to train this network, a rate distortion cost is minimized through gradient descent. The cost consists of a rate term plus lambda times the distortion term, which is usually the mean square error. And to train this model at different bit rate, a different lambda has to be used to train the rate distortion cost. The VAE framework compresses the entire image altogether into a single latent. But in some applications, such as video coding, it may be desirable to code smaller portions of the image into separate latents. In this work, we will analyze the effect of using VAE framework for block-based image coding, where we use block sizes that are much smaller than the image size. We used a fixed block size b by b to code the entire image. And for each image, we partition the image into small blocks, and each block is coded successively in the raster scan order, as shown in this figure. To train our models, we use images from the COGO dataset as the training data. We extracted 200,000 blocks, each of size b by b, randomly from the COGO images. After training our models, we evaluated on the Kodak image dataset, which consists of 24 color images. We code each Kodak image block by block in the raster scan order, and after the entire image has been decoded, we compute the PSNR and bits per pixel over the entire image. Here we show the results of directly using the VAE model to code images in small blocks. We use the same network architecture as in the joint autoregressive and hybrid prior model, except that we have less strided convolution layers. This is because our block size is too small. It cannot accommodate for that many downsampling in both the encoder and hyperencoder models. In this figure, we show the decrease in performance when we code in small block sizes. We tested two different models, one using a block size of 64 and the other using a block size of 32. The decrease in performance is more significant when the block size becomes smaller. We think that this is because spatial redundancy across the image cannot be fully utilized when the block is becoming very small. To overcome the decrease in performance, we utilize the decoded border pixels to extract information about the target block. Because our image is coded in a raster scan order, we have decoded pixels that are to the above and to the left of the target block. For experiments, we use a 16 pixels wide decoded border around the target, and we zero fill the regions that have not been coded. We designed a border prediction network to extract features from the decoded border. The first part of the network uses multiple convolution layers to predict features for the empty regions, and we selected the kernel size to be large such that the perceptive field covers the entire target region. And from this predicted feature map, we use the second part of the network to go through two more threaded convolution to downsample it to the same size as the latent tensor. We designed two different models where we utilize the border prediction network. The first one is latent residual coding. First, we extract information from the predicted border with the border prediction network. And with the predicted features y-board, we subtracted from the encoded latent from the encoder network. We quantize the residual and we compress it using entropy coding. The reason we do this is because we want to remove information which can be predicted from the border and remove it from the target latent. And intuitively, when y-board is very similar to y-latent, the residual will contain many zeros when quantized, which will reduce the bitrate. And at the decoder side, the same y-board can be calculated from the decoded border and added back to the residual. The resulting tensor is then passed through the decoder network to get back to the decoded image. Here we show some visualization of the prediction by the border network. In the middle, we show the output of the decoder network when we have both the border latent and the center latent. On the right column, we show the output of the decoder network when we only have the border latent. We see the behavior is similar to directional Intra-Prediction as in standard video coding. When the network sees an edge that enters the target region, it will continue to extend this edge. And similarly for this example. But for the third example, the network learns to continue this edge into the target region, but it has no indication that this object is inside this center region. So it cannot predict the presence of this object. The second model we propose uses Intra-Prediction to aid entropy coding. We utilize the border predicted features to help gain a better estimate of the mean and variance parameter for y. We use an entropy parameters network to take in the outputs of the context model, the border prediction network, and the hyperdecoder network to predict the mean and variance. We also utilize the border predictive features to help predict the mean and variance for the hyperprior Z. We call this model the BLIC model, which stands for block-based learned image coding. Because our images are coded block by block, there are discontinuities between blocks which produce blocking artifacts. To remove these blocking artifacts, we also used a post-processing denoiser, the DNCNM network, to help remove these artifacts and further increase the PSNR. We would like to mention some details about our training procedure. During training, the border prediction network needs to have borders that are compressed to take in as input to learn from appropriate examples. but compressed border is not available when we train the network from scratch. To make compressed data for the border prediction network, we use a three-step training procedure. First, we train the model with uncompressed border pixels. Then, with the model in one, we use it to compress images in COCO in a block-based manner. And with the compressed images in two, we draw new samples with which we further fine-tune the model in one. And we train the post-processing network using 20,000 compressed images, which is a mix from different lambda rate points. We train different compression models for different lambda rate points, but we only train one post-processing network for all lambda rate points. Here we compare the performance of different models. The orange curve in this plot is when we use the VAE to code small blocks directly without any border prediction. By using border prediction, we recover some performance loss in both the latent residual coding model, which is shown in the pink curve, and the Blick model, which is shown in the brown curve. By using border prediction to predict both the mean and variance, the Blick model performed better than coding the residual. And by using post-processing, we further increase the PSNR as shown in the red curve. Here we compare the performance of different block sizes. Both the model with a block size of 64 and a block size of 32 benefited from having the border prediction. And especially for the block size of 64, the Blake model recover almost all the performance loss and have the same performance as coding the entire image directly. Here are some example images compressed by our models. We can see that in the compressed image, before post-processing, there are many blocking artifacts. And after post-processing, almost all of the blocking artifacts are removed. Here is another example from the codec image set. To summarize our work in this paper, we showed that directly using the variational autoencoder model for block-based coding resulted in a decrease in performance. We proposed a Blake model which uses border pixels to help the prediction of entropy coding parameters for both the latent and the hyperprior. We show that our proposed Blake model can recover most of the loss due to coding in small block sizes. For future works, we consider extending our models to allow for a variable block size and also to extend the method of using Intra-Prediction aided entropy coding so that we can do a similar thing for interframe prediction and video coding. Thank you for listening to my presentation, and I'm happy to take questions from the audience.